Hello. Thank you for joining us for this section of the tutorial, Methods and Demonstration of LCOE and IRR Calculations, which will be ran by myself, Mike Woodhouse, and Kelsey Horowitz. A review of the topics that our team work on. In the upper left, you can see an overview of the component manufacturing cost analysis that Brittany and Kelsey went over earlier. System capital cost analysis that Vignesh just went over in the previous section. And today we'll be diving into some examples and technical details of project pro forma analysis. And that's what we'll be diving into in this section. So zooming in on that graphic and discussing the metrics that we'll be shooting for. They include LCOE, which you most likely have heard of. Another one, internal rate of return, which has some advantages that we'll discuss later. And then a newer metric for us, the levelized cost of solar plus storage, which is also a pro forma analysis involving cash flows. And on the bottom, you can see a graphical representation of the cash flows that could represent what occurs during the life of a PV project. Beginning with the cost shown on the far left, the upfront capital cost for the installation. So that's the time from scoping the project to getting it built and commissioned and finally generating power. So that would be T equals 0 in terms of kilowatt hour generation. Then another benefit shown on the top, in addition to the kilowatt hours shown, is any incentives that can be monetized, like tax credits are relevant in the US for year one. Also depreciation incentives, using a tax shelter there can have benefits for PV systems. And then also benefits are feed-in tariff or PPA revenues. We'll talk more in detail about that later. And residual value on the far right, that enters into the question of what is a PV system and storage system worth at the end of its lifetime. For example, do the components have any recycling value, or are they a hazardous waste issue? Or also residual value could also possibly consider the kilowatt hours that could be generated past the analysis period, depending upon how you define that term. Another cost to track over the life cycle, in addition to the upfront capital cost, are O&M expenses. And that includes preventative and routine O&M. That's routine O&M could probably be something like module cleaning if you have a set cleaning schedule. Preventative O&M could be vegetation management, things like that. And asset management, so that's managerial tasks for maintaining the payments to insurance companies and whatever have you. Then there can also be corrective O&M issues, battery inverter repairs. Unplanned weather events can also cause corrective O&M responses. So not all cash flows in a PV project are known ahead of time. You try and budget them and predict them as best as possible, but corrective O&M is another item that can enter into the picture at some point. So let's first talk about the capital costs for PV systems. That was covered by Vignesh, and I'll just summarize it again here. These are representing module pricing and total system pricing, more for the US market, not rest of world. So the pricing could look higher relative to rest of world. And then the breakdown of system costs that we derive for Q1 2020, coming in around 95 US cents per watt. So that's the capital cost that we'll be using in the model example that I'm going to go through. And I should have clarified that system is for cost model results for a one-axis tracking utility scale system. The next item is O&M, and O&M includes the preventative, planned, and unplanned items shown here, and there can be more that can happen. But here's a list of them in any rate, and we won't necessarily dive too much into the details of O&M for the purpose of this briefer tutorial. So now we have an overview of some of the pieces that go into the project pro forma. And next, let's talk about how one calculates LCOE and IRR for PV projects. And what we're going to step through is how to do this within NREL's System Advisor model, which is written within NREL's Strategic Energy Analysis Center, which our team is also within. So our team does work with the SAM team quite a bit, actually. And when you do LCOE modeling within SAM, there are two modes that you can select, and it really changes how the cash flow model works within SAM. The first mode is calculate the internal rate of return mode. This is within the SAM software. This is when you click the button for specify PPA price. This is the mode for when the PPA rates are set as inputs. So if you have a given PPA rate schedule, which could be very relevant to an actual project going in, and if you want to incorporate changes like merchant rates at some point in the pro forma, anything where there's the PPA rates are changing, it's easiest actually to do this in IRR mode. And so in that, you get to change the PPA rates over the time period for the pro forma. And then the IRR, by definition, is a discount rate for which the net present value of cash inflows, so for a PV project that would, utility scale PV project, that would most likely include PPA revenues and monetized tax benefits. And it's when the present value of cash inflows equals the net present value of cash outflows. So that would be the installation cost and the O&M expenses. So it's the what that means is that a higher IRR corresponds to essentially more PPA revenues or greater tax benefits, and lower installation costs and lower O&M expenses. The other mode that you can calculate within SAM is LCOE. And in that case, that's where you specify the IRR target. That is saying that the rate of return, still holding that identity, where the net present value of cash inflows equals net present value of cash outflows. So it's when that IRR is fixed and you are trying to calculate the PPA rate, basically, to achieve that IRR. And there are two different modes, but they have their advantages, disadvantages. It's not used as commonly. I actually see a lot of advantages in doing IRR mode, primarily because of the flexibility it has with inputting various PPA rates over the life of the project, and it's just more clear to understand the PPA revenue side. So when you run the calculations, solar resource obviously affects the result. That's intuitive. The production of more kilowatt hours, if you think about the simplified LCOE calculation, dollars per kilowatt, or just a simplified LCOE, dollars per kilowatt hour. More kilowatt hours increases the denominator, so that lowers the LCOE. In terms of cash flows, you can also think of more kilowatt hours generating more PPA revenues, but we'll talk about more about that later, and how that can improve IRR if you're thinking about it that way. But anyway, we all know that lower LCOE is in sunnier locations, and some of the lowest PPA rates that one will find are typically in the sunniest locations of the world. Now I'm going to step you through an example of how one could do a conceivable technology evaluation using LCOE IRR methods. And it's one where we want to examine the impacts of different module warranties on PV project economics. So what do I mean by that? Let's look at these curves. The top curve represents zero degradation profiles. So that would mean that the first year energy yield that you get from the project does not change over time. There's no degradation. That is a hypothetical, completely theoretical. I don't know that that's ever been observed in principle. So in practice, there is in silicon, there's a lot of times a year one D rate given on the module warranty data sheets. And really, these data sheets are perhaps marketing materials as much as anything. But looking at some module data sheets, we found one for an N-type module. And the N-type module had the lowest year one D rate given of just 2% that we could find. And then for mono PERC modules, for example, there typically seems to be a higher D rate. Some can be as low as 2%. But what we're using in this example is what I've called a conservative mono PERC warranty degradation profile. So this is, again, taken from a module data sheet, and I'm calling it conservative because it gives a high D rate in year one of 3%, and then a pretty high degradation rate, relatively high degradation rate of 0.7% per year for 25 years. That compares to the N-type module of 0.3% per year. So the conservative warranty profile is relatively high year one D rate, and then a relatively high degradation rate. One can find aggressive, you might call them, mono PERC warranty degradation profiles where there's 2.5% in year one, and then as low as, I've seen some as low as 0.4% per year as the degradation rate. So there are different warranty profiles offered by different modules, and this is not to say that N-type is better than P-type. Let's be clear. We're just looking at some warranty profiles given in module data sheets. And we want to translate that to impacts to PV project economics. So you can see this within SAM by going to the tab. It's within the SAM model called Lifetime and Degradation. It's when you're inputting the various input parameters within SAM. And then you'll see pop up annual DC degradation rate. You can use a fixed value, so that would be applying one degradation rate across all years. Or in this example, we're showing a higher D rate in year one because module warranties most recently, as far as I could tell, give a different year one D rate and then a higher year one D rate than the later degradation rate. So if you want to input those customized inputs, you need to go within SAM and edit the degradation schedule. Some tricks that I have found to do this include if you're doing it in Excel, if you're trying to program these numbers like 3, 3.68, 4.35, you can see going down. Maybe you've got a column of data in Excel. Sometimes it does not paste exactly into SAM, I found, and I have to go through the Notes app on a Mac. For you PC users, I don't know what to tell you. Hopefully you don't have these glitches, but there are some tricks to swap that from Excel to SAM. Hopefully you figure them out. I wish you luck. After you've input the degradation profiles into SAM, you can calculate the ProjectPPA revenues over the life of the project. And I'll show you in the next slide what this looks more within an actual SAM model. But for now, these are just results that you could create on a spreadsheet. You take the dollars per kilowatt hour or dollars per megawatt hour, more typically in utility scale, PPA rate times the energy yield times the system size. And that's how you calculate PPA revenues in dollars. Just look at the units and you'll see that things cross out and give you the units of dollars. So again, that's variable PPA rates affect PPA revenues at different years. And then energy yield, higher energy yield is going to create more project revenues. And then obviously bigger systems would also, in pure dollar terms, generate more revenues. So in this example that I've shown, we've taken the warranty profiles and multiplied those three factors over the different years. And just to remind you, degradation profiles are applied against the first year energy yield. So as the energy yield declines, the project PPA revenues declines. And so with those different warranty profiles within SAM, you would calculate these different revenue trajectories, and you can see a difference in lost revenues due to the different warranty profiles. Just to show you where this appears within SAM is what I'm... After calculating project revenues, the next step, the next line in the SAM cash flow model and a lot of other PV project pro forma models is project earnings before interest, taxes, depreciation, and amortization, or EBITDA. EBITDA equals PPA revenues minus O&M expenses. So this is where your O&M factors come in, is at the EBITDA stage. And what we've shown here, this example assumes $6 per kilowatt per year O&M expense. That's the year one O&M expense. And to that, we've added a 2.5% real escalator. So that is done after talking to some O&M service providers. A lot of them shared that it was their convention to express O&M costs with an escalator, typically understood in that on the order of 2 maybe to 5% per year. Presumably it includes maybe increased O&M expenses due to time. It's just like a budgeting for an extra O&M budget. Some people might hold O&M flat, in which case the lines shown in this figure would not be curved. They would be completely flat across the top. But if you look at this, even the zero degradation profile is curving down because of the escalator that we have included in O&M. Without an escalator, the zero degradation profile would be completely horizontal. Now looking at the other profiles, the warranty degradation profile for the N-type versus the P-type. Again, the N-type was projected to generate more PPA revenues than the P-type conservative profile. And so that also does translate to more EBITDA for the N-type. And so the P-type would have some lost earnings due to the different warranty profiles. Again, this is just a example system based upon warranty profiles, not saying at all that N-type is better than P-type, just looking at warranty profiles. So now you can see these results also in SAM. It's below revenues, as I mentioned. And EBITDA, again, it shows up as its own line item, and it's PPA revenues minus O&M expenses. Now, to be honest, if you are doing technology evaluation, I don't see any problem with stopping at EBITDA, because there you've caught all of the technology factors, essentially, including the degradation characteristics and also the O&M aspects. So the technical aspects of a PV project and storage project could possibly end at EBITDA. However, if you want to account for the interest, taxes, depreciation, amortization, so a lot of the tax side, the financing side, then you carry it some steps further. And then you can get to LCOE and IRR. LCOE and IRR are presumably after tax calculations, and so that factors into the next steps. And it is beyond the scope of this tutorial to go into all the different tax benefits and how to monetize them, even within SAM. Different workshop altogether. But just to summarize, like if you did want to go into SAM and input some representative tax assumptions, and I'll discuss the U.S. here. It's our understanding that a relevant depreciation schedule is 5-year MACRs. That's typical. And in 2020, it's possible to qualify for a 26% investment tax credit in the United States. Next year, it'll be 22% for utility scale, and then in 2022, it is 10%. So in the results that I've shown here, I did this over a 30-year analysis period, assumed a 95 cents per watt capital cost that was given in the earlier slide and from Vignesh. We talked about the O&M expense and the energy yield of 2,350. It's our understanding that's close to the mean. I believe that was from an LBL study. So when you do that, and you can do this totally, these results shown are actually SAM results. Using a $30 per megawatt hour fixed PPA rate, we calculated an improvement in IRR of 0.93%, or 93 basis points, and a lowering in LCOE by $1.2 per megawatt hour when the IRR is held constant at 6%. Now, if the technology generates more PPA revenues over the lifetime of the project, in principle, one could pay more upfront for the technology. It has a higher net present value. All of those PPA revenues in the future and EBITDA, higher EBITDA in the future, can be translated back to a net present value after taxes. And what I've shown here is just an example break-even analysis for this example shown here. And we calculate that the value of the different warranty profiles works out to be on the order of 5 to 6 cents per watt, which is quite remarkable if we consider rest of world module pricing nowadays, not US pricing, but rest of world is probably, as far as we hear, 20-25 cents per watt. So this is the value in the module, the value of the module based upon the warranty profile could be on the order of 25% or so of the total module selling price. So this is an interesting topic, we feel, going forward, diving into the total value of a module being more than just the initial price. I just wanted to, it is with some hesitation that I included this last slide, but I wanted to show an equation roughly for LCOE. And sometimes I think that as a community, we like to look at this because we're trying to simplify it and put it all on a PowerPoint or maybe something that'll fit within a paper. Really, LCOE and IRR calculations most likely involve spreadsheets and pro forma cash flow analysis, but sometimes we try and come up with an equation. It's an exercise in folly, if you ask me. But nonetheless, here is one. And the advantage of it is you can highlight some technical opportunities, like an installation cost, lower installation cost, lower LCOE, reducing the numerator. And installation costs can be reduced by improving efficiency, lower component costs, and then also you get a lower installation cost for fixed tilt versus tracking, for example, the system architecture. But when you do LCOE, you have to consider energy yield. And so maybe there again, if it improves energy yield and PPA revenues, it can be worth more paying up front initially. The other important part of LCOE is monetizing any tax credits. And so an item within this equation is depreciation. That's a significant tax benefit, can be. And another one within the United States anyway is the investment tax credit. But if you are not in the US and doing LCOE calculations, I would encourage you to also research what tax incentives can be monetized and would be relevant for your pro forma analysis, because it can significantly impact the results. The denominator, the capacity factor term, basically, energy yield. That is the kilowatt hours generated. So more kilowatt hours increases the denominator, lowers LCOE, and that, of course, is a function of the system location, the orientation, its tilt angle, whether it's tracking or not. Bifaciality is another hot topic now for increasing energy yield. Temperature coefficient plays, that's where that comes in. And low light level efficiencies, if that's relevant at all. So climate effects also affect the capacity factor term, and that's why greater solar resource equals lower LCOE. The other one, recycling and repowering. We didn't talk about that, but the recycling or repowering ideas could also factor into residual value. And also the residual value of remaining kilowatt hours if the project was ended should be considered. Another factor that's kind of reliability driven in an LCOE calculation, since the discount rate is fixed, is the PV module and system reliability. Presumably more reliable systems also have benefits in lower discount rates. They lower O&M expenses, and numerous benefits. And that is the end of my section. Thank you. And next I will hand it to Kelsey.
All right, now I'll walk you through two NREL tools that you can use for calculating levelized cost of energy, or LCOE. The first is NREL's System Advisory Model, or SAM. There's a link to SAM's website here. This has a lot of different features, including very sophisticated financial models, many different options for modifying the specifics of module and system technologies and designs. And for PV, the ability to pair with storage and look at how that could impact your project economics. This can and has been used in detailed site planning and analysis. And we also use SAM on our team for creating the benchmark LCOE numbers that come out in our annual reports. But some researchers find that SAM has a learning curve and can be a bit of a black box and difficult to accurately and quickly understand potential impacts of different R&D directions without potentially introducing some confounding factors if you don't really know what you're doing. So because of that, we introduced NREL's simplified online PV LCOE calculator that also has a link to it here. And this is a much more simplified tool. It's just online, and it's specifically targeted at PV researchers who want to quickly explore the potential impacts of different high-level R&D directions. This is also PV specific, whereas SAM allows you to calculate LCOE for a myriad of different energy technologies. It's not as accurate or as fully featured as SAM, so I wouldn't use this for detailed project planning. On the other hand, it does include some things that SAM doesn't, like a breakdown of the cost components within a PV module. One caveat to this is that it was last updated in mid-2018, which I'll talk about a little bit more when I demo the tool. And we are planning an update for this calendar year. So hopefully that'll be updated, and in the meantime, this can still give you a rough sense of potential value of different R&D directions. So now I'm going to go through and actually demo each of these tools for you. First, I'm going to walk you through the comparative PV LCOE calculator. I have the web address in the slide deck as well, but it's just nrel.gov/pv/LCOE calculator. And again, this tool is really meant to be a simple way for researchers to quickly compare incumbent technologies to different proposed technologies or R&D directions to get some sense of their potential value if you don't have bandwidth or expertise to really fully dive into SAM and make sure that you're getting a reasonable result out of it. So this is a somewhat simplified model. And this is what it looks like. So you can see there's this input section here, and there's a blue box called baseline, and then a green box called proposed. So this blue box baseline is basically meant to represent an incumbent technology that you would want to compare against. And if you click this presets button here, you can see that there's a few different baseline preset options to select from. So you can choose monosilicon, multi-silicon, or CAD-TEL, which are the technologies with the largest market share today. You can also select a package type, so glass polymer or glass, and a system type. Currently, fixed tilt utility scale, single axis tracked utility scale, and roof mounted residential scale are supported, so we don't have commercial ground mount or commercial rooftop in here at this time. And then you pick a location. So you can see there's one location per state. So the state is used to calculate the installed system cost for that state. And then the location corresponds to the point at which we are taking irradiance data to calculate the LCOE for this specific model. Okay, so say I want to look at a multi-silicon glass polymer backsheet single axis tracked utility scale in Kansas City, Missouri, and I click use this preset. It'll automatically slide these bars and adjust the values so that they match that pre-selected technology. And then if you want to do this, you can copy the proposed technology from the baseline. So this may be, for example, if you only have data about how one section of the cell or the system changes with your idea. So for example, you know that you have this new front layer that you've created that you think adds 60 cents per meter squared to the front layer, but you don't really have data on the cell cost, back layer cost, all of these different components of O&M and balance of systems, for example. And so you just want to use the presets that are equal to what is in the incumbent or the baseline scenario because you think that those will stay the same. Okay, so let's keep going with this example where I have a new front layer that I think costs 60 cents a meter squared more than in the traditional cell. And I think that for this, I will get a 0.4% boost in efficiency, but that nothing else about the cell will change. And so I can just drag these sliders and update the values. You can also type these in here if you want. So type in 470, 466, and the slider will adjust if you don't want to actually manually move the slider. And then if you scroll down here, you can see the baseline LCOE compared to the proposed LCOE, really trying to keep as many other assumptions constant as possible, like for example, the financial parameter of discount rate. You can see in this case, you get a very small savings in LCOE in this particular location because of that small boost in efficiency that you saw, which reduced the total installed system cost and the module cost. Module price. So one thing to note about this, and just to be careful of when you're doing research and trying to evaluate the value of that research, is that pricing does not always correspond to cost. So in this case, this is really the potential cost savings you could get for the balance of module materials like the front glass and the back sheet, etc. if you have that higher efficiency. But in reality, people may want to charge a premium for that module. And so you may or may not actually see this module cost savings. And similarly for the system installed cost, but this can at least give you some sense of the kind of fundamental value, potential savings in terms of module cost, system costs, and the LCOE of your proposed idea. Like I mentioned in the slides, one caveat for this is that the last time this website was updated was March 2018, so it's using about 2-year-old data for the system installed cost model. That system installed cost data actually comes from NREL's bottom-up cost models that are published annually in our benchmark report. We are hoping to make an update this fiscal year or by the end of this calendar year, and then you'll be able to see that if you look down in this section with the citation here. And those changes will reflect both changes to the pricing of the input materials, the installation process itself, and improvements to how our model captures impacts of efficiency on system cost. Okay, so that's this tool. Full walkthrough of SAM. This is in no way intended to be comprehensive or help you to be able to actually use SAM at the end of this conversation, but I just wanted to give you an overview, a sense of the look and feel of SAM and how it's different from the online PV LCOE tool that we just walked through. So this is the welcome page for SAM. I'm using the latest version, which is from February 29th, 2020. You can go up here and start a new project. You can see that SAM allows you to model a variety of different energy technologies, not just PV. If we look at PV, there's a detailed PV model, PV watts, which is only PV watts, and then high concentration PV. I'm going to click on the detailed PV model, which is what we use most frequently. And you can see you can look at different types of systems, power purchase agreements, or distributed systems with different ownership models and classes. If you select the no financial model, this just uses SAM's performance modules, so you can see the energy production for the system, for example, throughout the year, but it won't actually calculate the financial parameters or metrics associated with the system. So as an example, let's go through one of these single owner power purchase agreement systems. So here on the left, you have all the different tabs where you can specify the parameters of your system and its finances. So this location and resource page is just where you put in the location and resource that you want to use for the LCOE modeling and download the weather files here. And the module tab is where you put in the module specifications. So there's a few different options to do this. There's two libraries. One of them is this CEC performance model with module database, and you can see there's a whole bunch of different options here for commercially available panels from different companies that have the specifications already loaded in here. The other model with module database is the Sandia PV array performance model. You can click on help or just Google these different databases to get more details on what they are, what they assume, and how they're different. You can also just input efficiency versus irradiance here in the simple efficiency model, as well as other characteristics of the panel. Or you can enter your own specifications within this CEC performance model here, or use a single diode model. When we're doing techno-economic analysis for our benchmark reports, we typically use modules out of the CEC performance module database associated with the technology that we're looking at from a leading company or a set of leading companies. And then similarly, you can select an inverter from this database where they have information about inverters from many different commercial companies, or specify some of your own input parameters or load things off of an inverter data sheet. This is the tab where you input things like AC and DC sizing, the electrical configuration, tracking, and orientation. This is something you want to be careful with if you're doing these calculations. All right, there we go. Sorry. When I had selected that other option for the inverter, it had blown up the DC to AC ratio to something really unrealistic. So anyway, you want to be really careful when configuring all these parameters so that you don't get something crazy that causes you to get really high, really low LCOE values, but doesn't really have anything to do with what you would actually see for the economics of your underlying system with a specific module technology. So it takes some time to figure out how to configure all of these inputs. You can also input information about shading and more details on the layout of the array here. Losses, so losses by type. You can put in monthly soiling values by pasting in an array here or manually entering values. They just added this tab called Grid Interconnection Limits. So for example, if you can't output more than a certain amount here onto the grid, you can enter that here, and then it won't let you produce PV beyond that limit on the AC side. You can also insert an array of curtailment values throughout the year. This is where you input degradation rate and other information about the lifetime of the system. This is the system cost tab. So what SAM really cares about is this final value here, which is calculated based on all these different inputs. So one of the things that we try to do if we're doing a parametric analysis, for example, where we want to be able to just vary one cell easily and look at the potential impacts on LCOE, is you can set everything to 0 except the module cost and put the full system installed cost into this bucket, and then just vary the module cost using this parametrics tab down here on the bottom left corner, and see how that affects your LCOE. SAM does try to do a good job of configuring their defaults, not just for system cost, but for all these different parameters. So they take input from around the lab and other places, and so that these are should be a pretty good representation of some default sort of median value that you might see in a given year. It's always good to check those things as well. You also input your operations and maintenance costs here. This is where you configure your financial parameters. If you have no idea what these should be and you're trying to compare between technologies, it's helpful to leave these as the default. There may be some cases where you actually have a reason to believe that a certain technology would, for example, have a higher or lower discount rate if it's riskier and earlier stage, for example. And so maybe you want to configure those, but that's sort of an advanced analysis. This is where you can input information about the revenue. So SAM doesn't just calculate LCOE, it actually calculates revenues as well, net present values, payback periods, and things like that. So you can specify any compensation based on time of delivery, any capacity payments or curtailment payments if that exists, or specify a target IRR, an internal rate of return, or a PPA price. Again, going through this super fast, just to give you a sense of what this tool is. There is a lot more information and some resources I'll provide on the next slide about how to use SAM. And you can always click this help button up in the corner on a given tab as well. Incentives, federal, state incentives, and utility incentives, either production-based or capacity-based, and depreciation parameters. Again, if you don't even know what that means, just leave this alone to stay at the default value. So then you come down here and you click Simulate. And SAM creates all of these different output tabs. This is a summary that gives you some of the key metrics you might be interested in. So here's the nominal and real LCOE for this system, PPA prices, energy yield, capacity factor, net present value, etc. here. And they also have some nice summary charts that are automatically output. You can look for more detailed information on a specific set of data here by filtering through these values on the data tables. For example, you can look at losses, create your own graphs, look at the actual cash flow in each year for the system, plot some different time series values, look at profiles for each month of the year, for example, get some statistics, create heat maps. So you can see there's really a lot of sort of much more sophisticated capability in terms of both input configuration and reporting here, which can be good or bad depending on what you're trying to do. Certainly if you're actually trying to get a very accurate assessment of cost for a specific project, or get a little bit more into the weeds on some of the input parameters, this is a tool that will allow you to do that. I'm not going to go into these again just because we don't have that much time, but you can see down here in the bottom left there's also a lot of other cool functions with SAM. So you can do parametric analysis really easily here. You can do some stochastic analyses, P50, P90 analyses, and then you can also look at these different macros that have been created and run these. You're also able to create your own scripts in SAM, and there's a Python interface so that you can interact with inputs and outputs of SAM, run SAM through Python, which is pretty nice. So a lot of flexibility there. You can see this is where you'd create a new script. And then just to very briefly show you, if we look at one of these distributed options, it looks very similar here. But some of the things like these financial parameters, for example, are different because of the way that these systems are financed in the residential market. And then you can also input things like electricity rates for a given location, what type of metering there is, if it's net metering or net billing. You can actually search for rates here for different utilities. So I live in Colorado with Xcel Energy, so I can actually find their rates now. Just show the active ones and say I want to pick this time of use rate that they have. It'll download and apply that rate here. And you can also input the electric load each month or throughout the year. So this is a 8760 each hour of the year. And these things all affect the payback period and the finances for a distributed system that's co-located with a load. Okay. So now I'll just give you a couple tips for using SAM for PV R&D evaluation. Again, there are a lot of things that you should know, not just what I'm showing here, because SAM is complicated and you can easily convolute different effects if you don't know how to use it. So I really recommend diving more deeply into their documentation if you're interested in using this tool. I provided the link again here. You can see they also have a forum and people will answer questions for you. If you are interested and you do have the time to really learn SAM, it is a very cool tool that you can do a lot of analysis with. So just two things that I've noticed when using SAM for PV R&D evaluation. One of them is if you're trying to look at the effects of efficiency on LCOE, the only thing you need to change in SAM is the total installed system cost under the system cost tab, and that's per watt. SAM does not automatically calculate how efficiency influences those installed system costs, so you're going to have to manually compute those values or take data from our latest reports on this topic, which is what I would recommend, and then put it into that installed cost cell in SAM that we just looked at. If you do change the efficiency using that simple efficiency model in the module tab that we walked through, where you could change the efficiency at different irradiance levels, I've noticed that you can get some weird effects where the system design will change or the layout will change, and you can see things like the LCOE going up as efficiency increases if you change nothing else. And so you really need to know what you're doing and be very careful to avoid those issues. So I would actually recommend not changing that if you're trying to look at efficiency impacts, just leaving that efficiency value fixed or using a module from the module database that has other characteristics outside of efficiency similar to what you would expect for your technology, even at different efficiency levels. And that works out because LCOE is actually normalized both in the numerator and denominator by efficiency. So it's dollar per rated watt divided by watt hour per rated watt, and the rated watts depend directly on efficiency. And so you don't actually need to change those if you just update the system installed cost and leave everything else the same. You should get a sense of how efficiency impacts the LCOE. When you are picking that number to put in the installed cost box, I would recommend, again, using data from our most recent reports on this that use our bottom-up model. We've done some recent research that shows if you use a simple efficiency model where you categorize costs as area dependent or power dependent, and then use a simple equation to calculate cost per watt with efficiency from that it's not really an accurate representation of the savings that you can get with the higher efficiency or penalty for lower efficiency. And I have a lot more recent data on this that hasn't quite been published yet. I'd be happy to discuss with you if you have questions. A second tip for using SAM if you're trying to compare across technologies on a technology-only basis in the long term is to use a standard set of financial parameters. And again, if you have no idea what those should be, SAM does a pretty good job of configuring the default, so it's okay to just leave those as they are. But if you are trying to commercialize a new technology in the near term, just be aware that there could be some difference in financing costs as you're pricing in that initial risk of any new technology. So again, different ways to use this tool and the online PV LCOE calculator, depending on if you're doing more long-term research planning, try to kind of prepare data for proposals or understand at a high level if a certain research direction is valuable versus near-term planning for projects or technology transfer. All right, so that's it.